If you think back into the dim, dark past, back in prehistoric ages of 1985 or so, data languages, well, DBase was about all there was, at that point used a syntax which represented the actual structure of the data within the programming language. If you wanted to use a table named EMPL, well, you said use that table. If you wanted to replace the salary field and increase it with the value, you'd write a query which just said replace all salary with some new expression, and you could say a for clause, or that's a where clause in DBase world, where supervises is greater than 0. And then you could list all those values simply by just saying list all whatever. And of course, DBase didn't have IntelliSense, but if it had, as you wrote this code, those field names would have been brought up for you because the data was integrated with the programming language itself. If you flash forward to the beginning of the .NET world, we're going to skip the bad VB access days, just go right on to .NET, you might see code that looks like this. In this case, you'd create a SQL command, which includes a string which identifies the fields you want. And then, because we want to pass in a value for that supervises field, we would then use the add with value method of a parameters collection and specify a parameter name and value. You'd have to create a connection, again using some string, which I've replaced with just 3 dots here. We open that connection. We execute a reader and return back a collection of data, which we then iterate through with a while loop, calling the read method of that reader. And then for each field, use a string-based index into our data reader to retrieve back the fields we want. We could do something with those. Here I'm not displaying them, I'm just retrieving them. And when we're done, we would close the data reader, which, had we set things up correctly, would also close the connection. We didn't do that here, but could. In any case, in this code, as you can see, you have to know strings that represent the command, the connection, and each of the field names. There's no help from the programming language to make that happen. To make things a little better, you could use some sort of object relational mapping to create a class which represents the data. And then you might end up with code that looks like this. Now, I've used a very simple example here. Imagine you have a class named employee, which contains a property for each of the fields in your data. You could have code which would fill in some data structure based on that class. Here I have a create criteria method which takes as a parameter the type of structure it needs to fill in this case an employee instance, and then there's an add method to add an expression to define a where clause, and then a method to list through these things, and then we have a loop which uses properties of the employee class rather than string-based indexes into that employee class. But someone has to create the object relational mapper for this, and you're still using data-oriented constructs, not language features, to interact with that data. An object relational mapping provides a mapping between relational data to and from real objects. And it provides a cleaner integration of business rules and validation. So obviously, an object relational mapping makes it easier for you to write data-focused applications than just hooking up all the code yourself. Even given an object relational mapper, which actually typed data sets in .NET sort of give you, challenges still remain. How do you work with non-relational data? Maybe you want to work with XML data, or data that's coming in from an RSS feed, which is XML data, web service data, or REST service data, Active Directory, or files, or any sort of static data. What do? How do you interact with just a collection of plain old objects? How would you interact and query any custom domain model? That's really the question here. How do you enable clean code? And this is our watchword, what we're going for here. How do you enable clean code in both a strongly typed and a dynamic language world? As Microsoft moves towards more dynamic language as opposed to strongly typed languages, what do? The answer, at least from Microsoft's point of view, is LINQ. Language Integrated Query provides query, set, and transform operations for .NET. It makes querying data, and I mean any kind of data, a core programming concept built into programming languages. And it works with all types and shapes of data. You can use it with relational databases, with XML, and with just a collection of any kind of objects. LINQ works with all .NET languages, but both Visual Basic and C# have integrated language support, and we'll look at many of the language features that have been added to those languages to make LINQ work. Of course, it works with ASP.NET and any kind of Windows application, and you can also find third-party LINQ providers, including Amazon.com or eBay. Each of these can and might create a LINQ provider that makes it possible for you to directly access and work with their data without having to interpret it on your own. Now, LINQ and Visual Basic and C# makes it possible for you to write your data access code directly in either language. You get compile time syntax and schema checking, and you get IntelliSense too. There's really no need to create a query as a string as you might have before LINQ. If you do that, you have to wait until runtime to see if the query includes correct field names and syntax. Using LINQ, you know these things at compile time. LINQ provides data access code that's abstracted from underlying data. It provides a consistent syntax across various data sources. Throughout this course, we'll look at multiple different data sources, and you'll see everything you learn in this chapter applies to pretty much every kind of data access. You can even, using LINQ, join information from different data sources. If you need to have data come from an XML file, and then join that to data coming from a SQL database, no problem. LINQ can handle that for you. In order for LINQ to do its work, there were several language features that both Visual Basic and C# were required to add. We'll look at each of these throughout this course. These include query expressions, anonymous types, extension methods, lambda expressions, implicitly typed local variables, and object initializers. Both Visual Basic and C# add all these language features, well, and a little more, so you can type code within Visual Studio, get IntelliSense, and make it easy to create LINQ queries. LINQ provides hooks to many different kinds of data. For example, LINQ2Objects provides a set of methods that work against any collection that implements either the static or the generic version of the IEnumerable interface, an array, a list, a dictionary. These all implement the correct interface so you can use LINQ2Objects with those. And LINQ2Objects makes any collection of objects a data source. LINQ works with relational data as well. You can use LINQ2Dataset, which allows you to query and update data in an ADO.NET dataset. This is important because normally a dataset doesn't have a querying engine. Once you get the dataset filled with data, anything you do is generally in code you write yourself. There isn't a querying engine. For example, if you're an Access developer, once you created a record set in Access, you could use the built-in JET querying engine to work against that data. .NET never had that capability. But using LINQ2Dataset, you can now query over that dataset using LINQ and the standard LINQ features. LINQ2Entities allows developers to use LINQ to program against data that's exposed using the entity data model. That's a conceptual data model that allows applications to interact with data as if it was a set of objects or entities. You'll see more about LINQ2Entities later in the course. You can use LINQ against SQL Server. LINQ2SQL takes advantage of an object relational mapper built into Visual Studio to create a mapping between data and objects. And again, once you do that, you're pretty much just working with LINQ2Objects to interact with instances of a class that represents your SQL data. You can also use LINQ2XML. This provides a better XML document object model. When we look at LINQ2XML, you'll see there are a bunch of new classes in the .NET framework that make it possible, and generally pretty easy, to interact with XML, both querying and modifying and perhaps even creating new XML content. For those that appreciate a graphic diagram that explains how things work, you can imagine there are LINQ-enabled data sources including LINQ to objects, LINQ to relational data, and LINQ to XML. In the middle, we have our providers, which allow us to have LINQ to talk to the data sources that you see at the bottom of the screen. On top of this, we have the .NET Language Integrated Query, or LINQ. That's a layer of its own, and then each of the languages provides hooks into LINQ that provide language-specific features that talk to LINQ and then allow us to integrate and work with data. Let's look at these providers in a little more detail. LINQ to objects allows us to query sets of objects in memory. Things like collections, arrays, and lists can all be treated as queryable objects. If the class implements IEnumerable, or the generic version of that interface, you can use LINQ to query that collection of objects. LINQ to SQL allows you to query and modify data in SQL Server. You need to provide a mapping between a modeling class and a schema in your data source. And there is a tool in Visual Studio that will do that for you, although in this section and the ones that immediately follow, we're not going to use that tool. I'll show you how to do it in code first, and later you'll learn how to use the modeling tool. You can use the system.data.link.data context class to provide the plumbing between the objects and the actual data. And although you could use Visual Studio's Object Relational Designer to make it easier, for now we're just going to mark up the entity class manually. And you'll see it's pretty easy to do, although you'll generally want to use the designer that's built into Visual Studio to do this. And you probably won't do the manual steps you'll see when I work through it in the first example. The data context class manages the communication between the actual data and your LINQ queries. And it stores state for optimistic concurrency checks. The data context class does that for you. The linked XML provider makes it easy to query, modify, and generate XML content. You can work with XML from a file or from a stream. It doesn't matter whether it's stored on disk or not. And the system.link.xml.xObject, xElement, and xAttribute classes, along with others like them, make it easy to work with XML programmatically. These are new classes in the .NET framework added specifically for LINQ. The LINQ to XML provider works with these classes to create queryable collections of XML data, and you'll see examples of this in this course. Now, if you're a Visual Basic developer, I will mention that that language adds language-specific rich support for LINQ to XML that C# doesn't have in this current version. C# might catch up in a later version, but for now you should know that if you're using LINQ to XML, it's easier in Visual Basic than in C#. LINQ to Dataset allows you to query and update data in ADO.NET datasets. You can use the LINQ querying engine against data that's already cached in a client application. Now, strongly typed datasets are easier to work with than standard untyped datasets. In that case, you already know the schema, and it's just linked to objects once you have a strongly typed dataset. For untyped datasets, there's a few extra hoops you have to go through, and you'll learn about those when you study LINQ to datasets. Language features make it possible to query standard datasets, but like I said, it's a little more effort to make that happen. LINQ to Entities allows developers to query data that's exposed using that Entity Data Model, or EDM. And EDM is a conceptual model, which allows applications to interact with data as if it was a collection of objects, or, in other words, entities. Using EDM, ADO.NET exposes these entities as objects in the .NET framework and allows LINQ queries to operate on those objects. Conceptually, LINQ to Entities is pretty much the same as LINQ to SQL, but it works with any data source, not just SQL Server. And unlike LINQ to SQL, doesn't assume a one-to-one mapping between classes and the schema. It acts as a layer between the schema and the objects and can do all sorts of mapping between the schema and your objects in memory. It's a lot more flexible than LINQ to SQL, but does require more effort. Before we can create our own LINQ queries or study LINQ queries, we need to look at the structure of a LINQ query. A LINQ query contains clauses, a where clause, a select clause, an order by clause, that specify the data sources and iteration variables, variables that indicate how you want to iterate over the data. Obviously, there are from clauses that show where the data is coming from, and select clauses that indicate what you want to do with the data. Can also include things like filtering clauses, sorting clauses, there are grouping clauses or joining clauses to join multiple data sources, and there are calculating clauses that let you create calculated values. The from clause is required. It indicates the source of the data. Depending on the kind of query you're creating, all the rest of them can be there or not. But unless you indicate where the data is coming from, you can't create a query. Every LINQ query is made up of 3 stages. The 3 stages are, first of all, obtaining the data sources so you know where the data is coming from. Then you create the query in code. And finally, you execute the query to retrieve the data the query retrieves or to execute the action the query is supposed to execute. Either way, you need to specify all 3 of these things. Where's the data coming from? What is the query? And then execute the query. Now we have a very simple example to get started. This is going to work with an array as a data source and just retrieve all the numbers in that array whose value is greater than 5. Our first demonstration, called numbers greater than 5, has an input array called numbers, which is just an array of integers. And now we'd like to reduce that array to just those that are greater than 5. So our next line of code says var output numbers, and var is a new keyword in C#, which we'll look at in more detail in a later section. But for now, just think of it as a way to define a variable strongly typed without identifying that type. The compiler figures it out based on what it sees on the right-hand side of the equal sign. Here, from number in numbers, our original collection, and number becomes an iterator variable. It's a variable which loops through all the items in the numbers input array. And notice we don't specify a type for that value either. The compiler figures that out too, and that's not a bad thing. Where number is greater than 5, so we'll filter to only those numbers whose value is greater than 5. We'll order by that number in the output collection, and we'll select the number itself. Now we could have selected some other expression, like I could have said select number times 2. This allows us to project the data in any way we want in the output of running this query. Now at this point, LINQ has not executed the query. We've just defined the query. It's not until we actually iterate through the results here for each number in output numbers, and notice we here have specified the type, though we could have used the var keyword here as well. For each number in output numbers, let's print out the value of each number. The important thing to remember is by defining the query, we don't actually run the query. It's not until we need the values that LINQ and C# actually execute that query and retrieve the results back. Let's run this and try it. I'll press A for our first option here. Let's go full screen. And now I'll step into this procedure. And there's our array of numbers. And here we calculate the output numbers. And if I hover over it, you'll see that they haven't yet calculated it. Expanding the results view will enumerate the IEnumerable. We don't need to do that because we're going to do that in our for each loop. In our for each loop, we'll visit each item in the output of our query and display it in the console window. I'll press F5 to run full speed, and you'll see just the values greater than 5 in ascending order, sorted by the value of the number. And that was the point of this query, to retrieve just those values in sorted order. Now, of course, this is an extremely simple example, but it gives you a flavor for what a LINQ query might look like. In our sample, The data source was an array of integers. Remember, the first stage in a LINQ query is obtaining the data source. And because the array class implements IEnumerable, you can query against it. That is, it's treated as a queryable type. Just to introduce the concept, although we won't delve into it here, you could also use XML as a data source. You could use LINQ to XML to load the contents of an XML file or an XML stream, it doesn't matter. In this case, I'm using a file, into a queryable collection of XElement objects. And the code would look something like this. XElement.load, given a file name, loads the items into a collection of XElement objects. You can also use LINQ to SQL once you have a class that provides the object relational mapping. In this code, for example, we have a class named customer, if you'll assume that, and the code starts out by creating a new data context object given a connection string, which I'll retrieve from my project's settings, and it's named Northwind connection string. I'll take that data context object and call its getTable method, passing in, it's a generic method, passing in a type, which is the customer type, which indicates what kind of table it should retrieve, a table of customer objects. It returns back a table of customer objects, which I'll name customers. Now, just to be completely clear, on the left-hand side there, I could have used the var keyword. Var customers equals dc.getTable, and that would work fine. My tendency is to only use the var keyword where it's completely clear from the context what the data type will be. And in this case, it's not completely clear that getTable returns a table of customers. You could probably guess, but just to make it clear, I've included all of the code here. The next stage is to define the query, and you saw that in the sample we looked at, that numbers greater than 5 demonstration. Given a data source, you specify the query. This defines the information you want to retrieve. In our case, it was the number itself. And optionally, you can specify how to sort, filter, or group. We did a sort, ordering by the number itself, and a filter, we filtered for only those values where the number was greater than 5. LINQ queries generally look the same, no matter the data source. If we were looking for customers whose customer ID was greater than some value or whose state was equal to some value, it would just be a where clause, which identified the exact filtering we'd like to use. The third stage is query execution. The query definition itself doesn't execute the query. Instead, it just defines the query that will run when it's time for your code to retrieve the data. To execute the query, you need to run some code that forces the query reference to need the values, like a for each loop. And in this course, that's generally what we'll do. You'll see some examples later on which bind the query results to some user interface control. And in that case, it's the data binding that forces the query execution. In our examples, for the most part, though, we'll just loop through the results of the query, and in that execution, we'll force the query to go get the data it needs. Let's expand our view here. What if you need to return multiple values from your query? In general, you have two options. You can create a class that exposes properties that map to the ones you want to retrieve, and you specify a new instance of that class in the select statement. So it will fill in your instance as it projects the data from the query. Or you can just specify values in the select clause. In this case, the compiler creates a new type for you. It doesn't give it a name you'll ever know, but it gives it a new type containing just the properties you specify. So if you needed to retrieve multiple values based on the input, you could either create your own class or allow the compiler to do that work for you. This represents a language feature called anonymous types, which we'll investigate more carefully later in the course. For now, let's look at an example that shows off creating a class that will return multiple values for you. For this example, we'll be looking at information about files in the file system, and I might like to retrieve information about the name, the length of the file, and the creation time of the file. So I've created a class called MyFileInfo. I don't want to deal with the FileInfo class because it's got too many fields. I just want these 3 specific fields, so I have my own class I'll use, and will fill it with data from the FileInfo object that I use to iterate through my query. Now down here in multiple return values 1, there's our first example that shows how to create multiple values. And if you look at the syntax carefully, you'll see how this works. Actually, to make it simpler, I'm just going to run the thing. So let's press F5, and I'll press B to run this. And now we're in the code. And so this calls the getFiles method of the directory info object, passing in C:\/ as the folder I'd like to retrieve information about. Files should now contain an array of all the files in C:\/ That's what the getFiles method returns. Because an array is a queryable object, we can query over it using LINQ. I'd like to retrieve only the files whose length is greater than 10,000, and for each of those, I would like to retrieve the name, the length, and the creation time in the results of my query. I have a class I'm using, MyFileInfo, and so I'll say from item, each item will represent one file, in my array of files, where item.length is greater than 10,000. Remember, item here refers to each item in turn. As I loop through all the items in that input collection of files, we'll order by first the length, and then for files with the same length, order by name. This shows you can order by multiple fields in that order by clause. We're going to select a new instance of the MyFileInfo class, and we'll specify values for each of the properties in that class. So here, this syntax says select all of this for each file. And all of this says create a new instance of this class, fill in the name property with this value of item, the length property with this property of item, and this property with this property of item. So we end up with, for each file, a new instance of the MyFileInfo class with all of its properties filled in. Pretty cool that you can do that. So we'll define the query. We haven't run it yet. Now in our for each loop, we'll actually execute the query as the code determines it needs the values. And so as soon as we ask it for a value, it executes the query. And now we'll see that we can display item.name, and in this case, item represents one item in that query. It's important to note that even though we didn't specify the type for that variable, I used the var keyword, the compiler knew that it was of type MyFileInfo, that is, this type defined right here. It knew that because query returns a collection of those objects. And so, item is one of those types. For each var item in query, as soon as I get to this console.write line, it says I have to go get those files. And so it does the work, retrieves those for us, we loop through them, and you see we get a list here of each of the files. And you see the file name, the file size, and the creation time as well. We got all of that information by executing this LINQ query here, which created an instance of this type for each file it found that it needed to project into the output. In the previous example, you saw code that created a simple type named MyFileInfo. That type contained properties that were returned by your LINQ query. But why should you create a class to simply return values? Can't the compiler do this for you? And you should know that anytime I ask a question in that whiny tone of voice, what I'm saying is, yes, of course, the compiler can do this for us. I'm leading us into the next concept. And this is anonymous types. An anonymous type is a class that the compiler generates for you based on the fields you want to retrieve from your query. The compiler creates the type based on what it sees in your query select clause. You'll never know the type's name unless you look at the IL that's created by your application. You'll see that the compiler does create a type and gives it some obscure name that it uses while running your code. This implicit type definition concept, that is, not defining the type of the variable you'll use to iterate through the results of your query, makes it possible to work with that anonymous type. If we didn't have implicit type definition, we couldn't use anonymous types. Well, let's look at an example that doesn't create a predefined type. It uses an anonymous type to get the same results as you saw in the previous example. In the second version of the same procedure we just saw, I have one tiny difference. The code's exactly the same. I just copied and pasted it for the most part. But you'll see here, I just say select new, not select new my file info like here. Down here, it's just select new nothing. How does that work? When I say select new, the C# compiler says, oh, he's not going to specify what type to use. I'll have to make it up myself. And so it does. It generates an anonymous type, whose name I'll never know, with properties specified within the select clause. It'll create properties name, length, and creation time. And down here, item will be of that anonymous type. Let's prove it. Let me run this full speed. I'll choose here C. There we go. And now, let's step into this. Now again, this just defines the query, doesn't run it. And down here, if I look at item, well, let's go a little farther here. Let's get it defined. There we go. Item is an anonymous type that contains all the values we want. Name, length, and creation time. They're filled in. It obviously is some type. We don't know its name, so we couldn't use its name. That's why we have to have the var keyword, because there is no way from this code you could know the name of that type. You could look at the IL, that is the intermediate language for this code, and you'll see that type defined. But for now, we don't know its name. So we use the var keyword, and it infers the type from the results it finds in the query. Here, we'll run this, and you'll see we get the exact same results as we did last time. 4 files sorted by the file size, and if 2 file sizes were the same, the file names would be sorted alphabetically. So you have 2 choices. You can either create your own class, I called mine myFileInfo, and use it in the select statement, or you can allow the compiler to generate its own type, and then when you retrieve the values, use the var keyword indicating that you want the compiler to determine that type from the results of running the query. Either way, you get the same answer. This solution, using an anonymous type, is certainly simpler than creating your own type just to contain those multiple return values. As I've said many times, defining the query doesn't cause that query to execute. It just defines the query. You have to actually force the execution by requesting the data. In other words, creating the query doesn't return any data. It provides the potential for returning data. Now, you can take advantage of this deferred execution if you like. You can break your query into small steps without fear of multiple trips to the server for data, because you remember that no matter how many steps you break the query up into, it won't actually execute until you ask it to. This makes debugging simpler because it's easier to break the query up into small steps, look at the results of each small step, and then when you're done, you know that the entire query does what you want. We have an example that proves this point. We'll look at that example now. Let's start by looking at the double it procedure. Double it's pretty straightforward. It takes in a value. It displays results. Now, the display results procedure is just a simple wrapper I've written to write information to the console window. I like to do that so I could later change this application to run not as a console app, but as a Windows app, say, or a web app, and not have to rewrite any of the demonstration code. I would just have to rewrite the display results procedure to display it somewhere else. In any case, display results has multiple overloaded values you'll see throughout this demonstration. For this example, we're just passing it a single string to display, and we return as the result of this procedure the input value doubled. So nothing very difficult here. In our deferred execution example, we take an array of numbers, and now we're going to write a query which says, from number in numbers, here's our input, select doublet of number. So if you think about it a second, the output from running this query should be the input array, but every value doubled. We should get 2, 10, 6, 12, 20, 24, and 16. Okay, now, if the query ran when we define it, you should see display results run at this point. If the query definition doesn't execute the query but instead just defines it, we won't see these display results run until we actually retrieve the value. So which is it? This should prove the point to you. If we see results in the output window before we execute this line of code, we would have to agree that defining the query executed it. But since I know that we're not going to, I can unequivocally say that defining the query will not display results in the output window, even though it would look like we're calling the doublet procedure, which displays things in the output window. To prove the point, let's come along here, choose the option to run this procedure, which is D, and let me step into it. Okay, here we go. Here we obtain the query input, that's our array, and here we define the query itself, which is going to loop through all the numbers and select as the output the results of calling the doublet procedure, passing in each individual number. I hit F10 to step over it. Let's go look at our output. Nothing's there. I stand correct. So let's go along now and step into or run display results. I don't need to step into it. So display results does two things. In this case, we're passing it a string as a title and a query to display the results of. Now, displaying the results of the query will cause the doublet method to run, which will also display results in the output. So if I run this full speed, we should see here the results displayed from the doublet procedure, and here the item in the output of the query. And again here, as it retrieves the next value, it calls doublet and then displays the result. So you can see that nothing actually gets run until we ask it to execute the query and do the work by retrieving those results. Now, if you like, you can take advantage of this in your code. I have an example here which breaks my query up into multiple steps. Here, for example, I have first defined query as from number in numbers, order by number descending, select number. Doesn't really do anything except sort it in descending order. So we'll get 12, 10, 8, 6, 5, 3, 1. Okay. And now we could test to make sure that query works. And then you could take the output of that query and use it as the input for the next query. That could say from number in query, which were the results of this, where number is less than 8, select number. So that should give us the numbers that are less than 8 in descending order, 6, 5, 3, 1. Then we could take the results of that query here and select doublet of the number. So we'd end up with 6, 5, 3, 1 doubled, which is 12, 10, 6, 2. That should be the results. Now that would give us the exact same results as just running this one query, but this one query wouldn't allow us to easily debug the various steps of the query. If we'd written it this way, we could display the results here, display the results here, and display the results here to make sure that each step of the query was working correctly. Now for this simple example, we don't need to do that. My only point was that you could do this. Now remember, we've already proved that just running this query doesn't call the doublet procedure. It's not until we actually need the results that it calls doublet. So there's no point even executing this query because you know exactly what it's going to do, except I know you won't believe me unless I run it. So I will press F5, run full speed, and you see that either way we do the work, we get the exact same results. And because we know the query doesn't execute until we explicitly request the results, by calling that display results procedure, we know that you can do it either way, break it up into multiple small queries or write one big query. Either way, you get the same results. You can force a query to execute if you use one of the aggregate functions like count, sum, average, min, or max within the query. The .NET runtime has to execute the query in order to calculate those results. You also might want to immediately execute a query and cache its results somewhere. That is, before you use a for each loop. And to make that happen, you can use a method like toList or toArray. Those are methods of the query you create that cache up the results in some intermediate data structure. Each one of those methods executes the query and returns the results in a new data structure for you to use however you like. We have an example that demonstrates this behavior, that is, forcing the execution of a query at a point in your code so you can use that data somewhere else without iterating through it. Let's try this example to see how that works. The forcing execution procedure takes in an array of numbers 1, 5, 3, 6, 10, 12, 8 and selects doublet of number. So we'll double each value, and that's the results of the query. Now, if you want to force the execution right here, we can call the toList method. That will execute the query and put the values into a new list of long. Well, let's run this thing, and we'll talk about it as we run it. I'll choose F, forcing execution. Here we are. Here we are in the code. We create our array. We set up our query. And of course, even though the query is set up to call doublet for each value, it hasn't done it yet. There's nothing in the console window. Here, I'll call the toList method, which will execute the query, get the results, and store them into a list of long integers. To prove a point, console window now shows the results of calling that doublet procedure. We were about to double each number in turn. Now, you could have also written that line of code as var items, as opposed to list of long items, and the code would have compiled and run just fine. My rule of thumb is I never use the var keyword unless it's completely clear by looking at the code what the type of that will be, or I have no other choice, as when working with an anonymous type. In this code, that line of code would have worked, but it's not easy to understand what items would have been, so I defined it explicitly in my code. Now, just to prove a point, I want to show that we can redefine what query is and get different results even after we've executed the query. So here, we'll see the results in items, and we'll see the results in our query. You see, items contains 2, 10, 6, 12, whatever. And our query, when we execute it, both calls doublet for each number and adds 10 to each number before it doubles it. So you see that as we execute the query, we have the calls to double it and the results for each item in the input array. So you can do both things with the same query, that is, convert it to a list or to an array by using toArray or toList. You haven't invalidated your query. You can run it again and do something different with it the second time.